Hi everyone, welcome to PCB Coffee Talk. I am Tara Dunn with Omni PCB.
And I'm Elizabeth Foradori with Omni PWV.
During our sessions, Elizabeth and I talk specifically about things related to printed circuit board manufacturing. Today we'll be chatting with Mike Brown of Interconnect Design Solutions about what he calls flex to fit.
Mike, thanks for joining us today. Can you explain the flex to fit concept?
Hi Elizabeth, hi Tara. Thank you for having me today. So the concept of flex to fit is really the ability to design a flexible circuit along the contour of a part when there's not ample space in a conventional approach. So what we're really talking about here is we're really talking about the convergence of the mechanical world meeting the electronics world. Before, they were two totally different disciplines, and as the migration of products and engineering come together and things get smaller and smaller and smaller, we really are seeing a convergence of the two different disciplines coming in as one. So the idea behind flex to fit is basically to be able to take a mechanical part and be able to extrude that surface and conform to that surface in order to create a flex circuit that'll fit within the confines of a given space or cavity.
Could you give us a specific example of how you've used this technology recently?
So if you look on the next slide, what we have here basically, and what we're emphasizing, is the ability to digitize a given part, and that digitizing has been around for a while. We can either scan it or digitize it mechanically, and what you're seeing is a bottom valence of a car, of a Porsche. And what we did is, once we scribed that piece part, we brought it in and created a 3D mechanical model. From that 3D mechanical model, what we can then do is we can actually lift that surface, because then we have an actual model to work with. We can lift that surface off, and then we can flatten it back out in the mechanical tools. There are different features within tools such as Pro E and SolidWorks that allow the surface to then be flattened using the sheet metal bending tools within those tools. And then at that point, we can then take and translate that into the ECAD environment to actually lay out the circuit board, because as you know, circuit boards aren't fabricated in a 3D environment. They're fabricated in the flat. So we have to have the ability to then flatten that surface back out. Now, the benefit of that is we get all the proper bend radiuses that are accounted for and the added length. We can also take and let's just say if you have a really tight radius, we can actually cut away portions of the flex to reduce the amount of adhesives and actual pieces of, say, Kapton, in order to make it more flexible and more permeable in some places versus others. So the tighter the radius, the lesser number of layers and the thinner amount of copper you'd really like to have. And we can analyze that and determine if we need to cut away some of those pieces or not. So case in point, what you're looking at here with this valence is we wanted to add sensors down in the bottom of the Porsche for various reasons. And we can actually take a flex circuit and mold it to the backside of that valence. So what we're doing, what's gained in that particular case is the cavity is very thin, very difficult to run wires, and then not to mention you're actually saving some weight versus, say, a conventional wire bundle.
So just to summarize, Mike, what are the benefits to this approach?
So some of the benefits where the space is limited and weight is a concern. So good examples would be, say, for an aircraft or drones, as they're so popular nowadays with autonomous vehicles. Basically, in the case of, we'll just say, a drone or fixed-wing aircraft, you could actually take and model the inside of the wing, per se, and use that cavity at that point to free up space. Because the problem is, let's just say a wire bundle that would otherwise go into its place takes up too much room and takes up too much weight. So by using a flex circuit in place that actually conforms to the inner cavity or the inside of a wing, you then open up that cavity for other features that may need to be added, whether it be for added sensors for monitoring or enhanced functionality into that cavity that otherwise would be occupied with larger wire bundle that you would not be able to have whatever additional functionality you wanted to add in.
So Mike, what would be some of the possible applications?
So as we mentioned with autonomous vehicles and drones, those are two examples. Other applications would be in the military, DoD space, the fuselage of planes, aircrafts, missile defense systems, things of that nature, where again weight and space is critical. Other applications that we're starting to see a trend kind of leading to is in the wearable electronics. Let's just say, for example, rather than run a bunch of wires in a shirt, with all these sensors in it, it becomes a bit bulky and a bit kludgy. So what you could do, rather than have wires that get sewn in, is you could actually sew in flex circuits that have been basically modeled or molded around the human body. And then at that point, those flex circuits could actually be sewn in between pieces of material. At that point, it's seamless. So it's not looking like you're wearing this Terminator style type shirt or something like that. It's actually nice and smooth, and it looks like regular clothing at that point. So we're seeing a trend in the wearable electronics market as well.
Mike, thank you so much for sitting down with us today. This has been a great discussion. Your contact information is being shown on the screen, and there's also a link to your website at the end of our written column.
We hope that everyone enjoyed this session and that we were able to provide information that will help you with your flexible circuit designs. Remember, designing and purchasing printed circuit boards should not be difficult. We hope you can join us for the next PCB Coffee Talk.